have internet, we should really worry about them. Maybe we should do something. Okay, so so you guys also, when will be the quiz? Sorry, what is it? When will be the quiz? Please keep it on Monday. We have truckload of labs and assignment. Okay, fine. We can do it on Monday. No problem. But tomorrow there will be lecture. Monday we can do it on quiz. No issues. But yeah, so you guys should practice a lot. Like I think if that is happening or not, I don't know, because it's also your responsibility partly to learn more. I can here only point some examples, but if you are really interested, you should go through the book and do more examples. Okay, so now let's get started about this non-deterministic finite automation, or NDFA, or NFA, sometimes people call it. Right, so this is also known as NFA. So what happens here? So we have seen last time in the last lecture, there was one example where this NDFA is like behaves in a crazy way, and it can go like so. Let's take the same example. What was it? So we have Q1, 0, 1, and in 1 it can also go to Q2, and Q3 is 0, null. Right? So null means without reading anything, you can go to Q3 from Q2, and similarly 1, Q4, 0, 1. So here, for example, the 0 transition for Q3 is missing, right? That is not given, but that is perfectly fine, right? So it's like it's not going anywhere of these, right? So that is like so Q4 is a finite state. But in DFA, you always have both the transitions, right? So you for every state, all the symbols it should read and behave something. Here in Q3, if you note, right, Q3 we are only having one transition. 0 we don't know really, right? It's not there, it's not defined, and that not missing definition is perfectly fine in NFA. Then there is another thing here. You might be observing that Q1, by reading 1, you can be in Q1, right? The same loop can be in Q1, or by reading 1, you can go to Q2. So there are multiple possibilities. So if you look into this, this looks like a parallel computation, right? So parallel computation where multiple independent processes or threads can be running concurrently, and if one of them reaches to the final state, we say final, this NFA accepts that symbol. Okay, that's the string. So given a string, just you feed it, and this can run in a parallel way, right? So you can think it as a parallel computation, or parallel computation where some branch of this parallel computation can take some different paths, some can take different transitions. So if every branch can take some different transition, and if one of these path, if you reach to the final state, you say that a string is accepted. Let's take an example to understand what I'm saying. So let's take an example. Let the string is 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0. Now, given this string, right? So this is a string. Given this string, how this NFA will operate, right? How, because in DFA it is very simple. DFA, there is only one single path from which will be there, and the one sequential single path. But in the NFA, there will be multiple paths, so it will look like a tree. How will it will look like? So the root node of this tree will be Q1. So because that's a start node. So in Q1, now you are going to read a symbol. Let's call it 0. So that's the symbol you are reading, 0. So let me write that here. 0 is what I read. So when I read 0, what will happen? Anyone? When I am in Q1 and read 0, what will happen? It will remain in Q1, right? So it will remain in Q1, and I can draw like this. When I read 1, now here it will be like two threads happening. One is it will remain in Q1, right? So there can be multiple things happening actually. Let's look into that. So one is it will remain in Q1. One is it can go to Q2, right? Or it can also go to Q3. Why? Why it can go to Q3? Because from Q2 to Q3 is nothing is required, so it can just change, right? Null, what is null? It will not, yeah, because of null string. Null string is like, null string means without doing anything, you can just jump to Q2 to Q3, you can anytime jump. So that means it can go to Q1 to then Q2 and then Q2 to Q3 and it can jump, so it will go to Q3. Okay. Next, we have 0, right? So we have a 0 next. Now, all of this branch we will separately compute. So Q1 0, you know that Q1 0 is Q1, right? Q2, if I read 0 in Q2, I can only go to Q3, nothing else. In Q3, if I read 0, what will happen? Nothing, right? So the Q3 0 is not at all defined. So we will stop there, no change. It will stop there. It will remain in Q3. That will die there. That no further things will happen in that. So 0 we have read. Now we have to read 1. Right. So this is the string we are reading. So this is the string we are reading. So we have read 0 1 0 1. So 1 when you read 1, again there will be a branching, right? So when you read 1, there is a branching. Again there will be a branch of 3. And this will be like Q1, Q2, and Q3. In Q3, if you read 1, right, you will go to Q4. Q3, you read 1, you go to Q4, and so on. And I'm not doing the entire computation, but if you can do that, this will be like multiple branching happening at every place, and there will be a large tree. And in the leaf, there will be, if there are in the leaf of this tree, right? If there are some final state, then we say that this string is accepted. So in book there is an example, and this example is exactly same example is given. So if you reach in the leaf node, if there is one of the node is a final state, we say that this NFA accepts this particular string, right? And this is why it is a parallel computation. We said looks like a parallel computation because you can do these things parallelly, these things parallelly, these things different branching parallelly. And if one of the branch reaches final state, we say it is final state. Now, what is the advantage happening here with this NFA? So one of the advantages is you really do not have to deal with lot of states in NFA, and you can do the same thing which you do in which you do it in so sorry, I just missed something. So what I was saying is, in NFA, like if you are asked you to make a DFA for something, you will have like lot of like complex things here. You might have to do like lot of states you need to deal. But NFA is very simple, and you can do and make NFA very easily. And then there are ways to convert NFA to DFA. We'll see that. But let's take an example. What I'm saying again to understand. So one of the example is you are asked to draw an FA, right? Draw an NFA. Draw an NFA for a language for which contains binary strings containing one in the third position from the end, containing one in the third position from the end. Right? From the end, it should contain third position from the end, it should contain one. For example, it should accept 0, 1, 0, 1, 0, 0. Right? Because in the third position, this is first position, second position, third position. Third position, there is a 1. From the last, there is a 1 in the third position. Similarly, it should accept 0, 0, 1, 0, 0, but it should not accept 0, 0, 0, 1, 0. Right? So this will not be accepted. This should be accepted. Right, so this is a question, and if you are asked to draw an NFA for this, how will you proceed? Very simple. You can proceed that I can do this. So Q1, right? Because I know that from the end, right? So this is 1, this is 2, 0, or 1, I don't care, 0 or 1, I don't care, and I am done in Q4, right? And if I have more zeros and ones, I don't care, 0, 1. Right, so this is enough, right? This one, which is NFA, this is enough. I don't have to say what happens when in Q4 0 or 1 is comes up. What happens when there are multiple zeros and ones? I can stay for ever in Q1 and then move in Q1 and then do the operation, right? So this NFA is very simple. But if let's try to think, how do you do this same question or same problem using DFA? That will be not easy. It's not very difficult, but it's like a lot of things you need to do. Yeah, so it's that's the beauty of NFA, you know. So Tushant, this is like you do not have to care all the conditions, what happens after that. If you take any string, so this NFA will accept, what is that? 1, 0, 0, 1. So 1001, will it accept? It will not. Right, so it will remain in Q1, means you can always like choose like that, right? So it will only accept those strings where the third position from the end is 1. Why? Why? Now, how will you accept 1001? Let's 100. No, so there is a confusion here. Okay, let's also clarify that. I think yes, good point. So here, like one thing also you should notice that when there is no definition, right? If there is no definition, so let's, for example, in Q4 there is no definition, right? So when you do, it doesn't. I think yeah. So that is, let's make clarify that. I think so. From like I read 1, I can go to Q2, right? If I read 0, I can go to Q3. If I read 1 again, I go to. Oh, sorry, I read 00, so I go to Q4, and then Q4 there is uh, no transition, right? So that's yeah, that's it should go to the null state. That's correct. So that if you are, it will. So I think I made a mistake while saying that when there is no transition, like so if I do not define a transition here, that means it is going to null state. It is not staying in the same, right? So it is going to null state, or let's call it a dead state or something. So this means that 01, it is going to dead state. It does not stop. Right. So when you read 1001, you will go to Q4, and then till 100, you will go for to this one, and then you are terminated. Right? What happens when you do? So I can not do that. Yeah. Is there any question? Tosant, is that clear or? But we don't need to draw dead state. It is assumed in, yeah, that is assumed. So assumed means, okay, when we will define it formally, it will be more clear. But yeah, so whenever we do not have a transition, it automatically, it means that it is going to null state, and we don't have to draw it in NFA. So this NFA is correct, and this NFA will do the job what is required, and you really like do not have to worry like a lot of details while drawing this NFA, right? So one thing is just 101, and then because what is it saying? If you read the question, it is saying that binary string containing 1 in the third position. So in the third position, it should be 1, right? And after that, I don't care. I don't care. 2 positions, I don't really care. And before that also, I don't care, right? So this is you drawn, and then this is for 01, and this is this, and this is this. But here I don't care, but I want them to be in 2 different position. But here position also I don't care. So in these 3 things, you can see that how do you draw a NFA? So this NFA is perfect, but how do you draw a DFA now for the same thing? Let's try to do that. So DFA for the same problem. What is happening is we need the 1 in the third position from the end, right? What are the possibilities? Let's take that. So 1 is either, let's call it Q000. That means 0 is in third position. Then Q100, 1 is in third position. then Q, so there will be eight position, eight states, right? So 2 to the power 3. These are all eight states because there are eight such strings where if you are looking for the third position one, right? So third position can be one or third position cannot be one. Means it is one, third position is one or third position is not one. So if third position, if you are looking, we need to have all these states. Now, among these, some of the states are final state. Which one of them are final states? Those having one in the third position. For example, this is a final state. This is not a final state, but this is a final state. Then this one is not. This one, 101, is a final state, and this is a final state, right? So these are the four final states, and what will be the initial state is like here, right? So this is nothing great. So start from there. Now we will have to define 0 1 transition on each of them, and if we can define that, we are done, right? So we need to define 0 1 transition on each of them. So what happens when you read 0 in the first? It will remain here because how many times you read 0, right? It will be in the self loop Q0000. But if you read 1, right? So if you read 1, then it will go to Q001. Yeah. Right. And similarly, you need to draw it for all of them. Like let's say in Q11, if I read 1, what will happen? I will remain here, right? If I read 0, then what will happen in Q111? If I read 0, what will happen? This one, like you can think like this, right? So 111 will become 110, right? So simply append that. So it will go to Q110, right? And similarly, if I do in Q110, if I read 0, it will become 100, right? If I read 0, it will become 100. If I read 1, it will become 101. You're getting what I am doing? Just whatever this is subscript is, you append that is symbol, right? So if you append that symbol and take the last three, it will do, right? So if you, like for example, 001, here it is 001. Now 001, I'm talking about this particular state, 001. In 001, if I read 1, I need to append 1, so it will become 011. All right? In 001, same state, in the same state here, if I write 001 and if I read 0, it will become 010. So where is 010? This guy. And I'm not completing this. You can easily now complete, and you will have a lot of transitions. For every state, you will have 2 transitions you need to define. And this complex, like multiple state diagram will do your job, and it will only accept those strings which ends with which has one in the third position from the end. And as you can see, this like DFA is like a lot of states, but the NFA for the same task is just 1, 2, 3, 4. 4 states, not much of a deal, and so on, right? So this is very simple. Like so, this is one of the advantages of in dealing with NFA. There is a question. There will be only 2 self loops. Yes, correct. That is correct. Because whenever the self loops will be only in the Q00 and Q111. Other places there will not be self loop. There will be a change of state. Maximum 3 transitions. Okay, so this this is not complete. Please complete this. But this way you can easily complete. Okay, so now let's take one more example of what is the advantage of NFA to appreciate NFA a bit. So let's say I have only the unary alphabet, or so let's say my alphabet is just 0, and I want a NFA, an NFA that accepts all strings which are either which contains either multiple of zeros What is it saying? Multiple of 3 or multiple of 2 or multiple of 3 number of zeros, right? So it should either contain 0 zeros like empty, or it should contain 2 0 or 4 zeros or 6 zeros or 3 zeros, 6 zeros, that is already there, 9 zeros, and so on, right? So this will contain, this should contains multiple of 2, it either contain multiple of 2 or contain multiple of 3 number of zeros. And if you remember our last lecture, if you have to draw DFA for this, how do you draw DFA for this? Can anyone tell me? This is like a union, right? So this is union of 2 DFAs, or a union of 2 languages. One language is multiple of 2, and like you can draw like for a multiple of 2, you can draw it for multiple of 3, and then for combining you need to take Cartesian product, and then using Cartesian product you will have multiple states, and you can deal with that, right? So you can easily draw a DFA for this particular example. Everyone with me? Any doubt how to? Anyone has issue with the drawing DFA for this particular example? Multiple to 2, and so you will draw for multiple. If you know how to draw DFA for multiple of 2, you will draw that. Then you know how to draw DFA for multiple of 3, you can draw that, and then you can take the Cartesian product logic and what we discussed last time, and then you will have you can draw a DFA for this. So how many states will the DFA will have for this particular example? Not NFA. DFA of this particular example, how many states will have? 6, 6, 3 into 2 into 3, 6, yeah. 6, correct. So it will have 6 states. Uh, of course, we are not reducing state here, but NFA, we can do following. So NFA, what we can do is first let me draw the DFA for two states, right? Sorry, first part, multiple of two. Multiple of two DFA will be like this: 0, 0, final state. This is multiple of 2, right? This is perfectly fine. Multiple of 3. 0 is a multiple of 3. 1 is not a multiple of 3. 2 is also not a multiple of 3, but 3 is a multiple of 3. So this. So this is for multiple of 2. This is for multiple of 3. I want to combine this, right? So we said that it is either of this. So what I will do is I will have a start state Q naught, and I can have a null transition here. Done, right? So this is perfectly fine as an NFA, and this NFA will either do the multiple of 2 or multiple of 3, because NFA is a god, right? So it knows which branch to execute when. So if it has to check, if it has to check like it is multiple of 3, it will go in the bottom branch. If it has to check multiple of 2, it will go in the top branch. And because this is NFA, and this will do, and this will work, right? So you will see that all that logic of what we tried to do is in Cartesian product and multiple such things is becoming very simple here. Just you are in Q naught and you are God. You know how to where to move. You can either given a string, you know where to move, and you will move to the right place, and you will check multiple of 2 or multiple of 3, right? So and then this completes the NFA for this particular example. Any question on this? And now at least I hope you are appreciating the power of NFA. Hopefully. Okay, good. So now let us define what is what do. So that's what, there is nothing like that, right? So this is the non-determinism advantage, right? So that's why I said it is God which knows where to. That's correct, because it is God, right? So it is God. So that's that you don't have to really worry about where it goes in NFA, because this is non-determinism, and just that given a string. One of the branch will run, because I actually that's just for a fun I said it is God, but actually what you do is you run all the possible branches, right? All the possible branches in the parallel manner, and if one of the branch is reaching final state, you say that is reaching the final state, right? So what just to make this is just out of sense of humor, I said it is God, but it is actually what it does is it will run all the possible branches, and as I discussed in the tree manner, and then even if it is reaching one of them, it's fine. If it was and there in place of either, then where will we make connection? I don't know. What is this? What does it mean? Nirvay, I'm not clear about what you're saying. Maybe you can elaborate. But by the time, or if you can take it offline if you want, also, or you can elaborate it now. But now let me define what is this NFA, non-deterministic finite automation, right? NFA in a formal way. Oh, it should be multiple of 3, 2 and 3 both. Oh, so you are okay. So if you are asking to design such NFA, which is multiple of 2 and 3 both. Yeah, we are not doing that. Here we are or and you need to think. Right? Here we are doing or. And if it is and, you need, but it's possible. I think you can definitely design for and as well. So you can try that doing that. Okay, so now let's define NFA. So sorry, non-deterministic finite automation is again a five tuple. What are the tuple? Q, sigma, delta, Q naught, F, where 1. Same thing, Q is a finite set of states. Second, sigma is a finite alphabet. And third is the major thing which is different. So delta. Now what is this delta? Delta is from where to where? If you remember in the DFA, we have this delta which is from Q sigma to Q, right? In the DFA. Here, yeah, it's not theta, it is Q. So Q, yeah, maybe it's looking like theta, sorry for that, but it's Q into sigma union null, because sigma does not contain null, right? But this guy can also take null, right? So this guy can take null. So this is sigma into null, and this is P of Q, which is a power set of Q. Power set of, right? So it can go to, potentially it can go to power, any like power set of Q, any of the subset of Qs, a subset of the set of states. And since power set of Q also contains null set, therefore it can also go to null set, and that's what we just were just discussing. If it is if the things are not defined, we assume that that is going to null set. Right, so this is what the difference is, and the rest is same. You have Q naught, which is Q, which is a start state, each the start state, right? Because why it is the, because it's only one. And fifth is F is the subset of Q, is the set of final state. Except for final state. Okay, right. So this is what is the NFA is. Only difference is 0.3, where the transitions are like defined like this. Okay, so let's take one more the same example and try to draw tabular representation of this. Right. So our first NFA, what we discussed again. Let me draw that. 1, 4, 0, 1. How much time we have? We have 5 minutes at least. Right. So this is an NFA one. Now this NFA, if I want to define based on what you have just defined, what are the, can anyone let's tell like what is Q? Q is a set of states. What is Q here? It is just Q1, Q2, Q3 and Q4. Right? This, what is sigma? Sigma is just 0, 1. Right? That is and what is start state? Is Q1 and final state is Q4. Right? It is a set, so that's therefore it is Q4. And what is delta? So delta, you can define the delta in a tabular form, in a table form. Let's draw that. So here we have the input, right? So 0, 1, sigma. Here we have states Q1, Q2, Q3, and Q4. Q1, 0. Q1, 0. What happens? Q1. But as you can see, I'm writing it in a set form. Why it is written in set form? Because the transition function is defined like that. Transition function is from Q to sigma to power set of Q, right? So therefore this is in set function. And if you have 1, now this guy will be Q1, Q2. If null, it is not defined, so 5. Right? If null is not defined. Similarly, for this one, Q2, you can make it Q2 to Q3, and then this is null, and then this is Q3. Right? And similarly, this is null, and this is Q4, and this is null. Similarly, in Q4, 0, you are doing Q4, 1, Q4, and this is null. Right? So this is a tabular representation of the transition function, and this is how the NFA is. Okay. So question for before we stop today. Question number 1 is every DFA is an NFA? Yeah. Is every DFA is an NFA? Yes. Right? Everyone will agree because there is nothing. Like so, DFA is like NFA looks like a slightly more powerful than NFA, but you can always, if I draw a DFA, it will always fits. Instead of power set of Q, what we have is you have Q itself, right? So which is a valid thing. Q is QA. Only thing is not there is perhaps this null transition is not allowed, but that's okay. Yeah, you can say like DFA is like NFA without null. Correct. Okay. But the next question is every NFA is a DFA? Yeah, but there is a surprise here. This also is yes. And this is what we are going to do next class is actually whatever you have done, this is a theorem which says every NDFA has an equivalent DFA. So I don't know whether this is right to say yes, but this is the like every NDFA, right? So whatever you are doing is NDFA, you can always make a DFA equivalent to that, and they are equally powerful in that sense. So it's not like you can do lot of things with NFA. At least when I say this, let's call it is every. This may not be right way to say. Can we say like NFAs and DFAs are same equally powerful? Right? They are equally powerful because every DFA. Yeah, yeah, correct. So that's it's not that is what Osand is saying is powerful. Yeah, yeah, that's a good question. What is the definition of powerful? Powerful means we are think recall that what we are talking about is what language is accept. So if you remember our discussion that this is where we are in the set of states, set of all languages. This is the regular language. Can NFA do beyond regular language? Yeah, yeah. So the answer is no. Don't. Yeah, maybe it's not like let's not confuse with the answer. But I'm trying to say is NFA and DFA more or less means they are equally powerful. And what I'm trying to define now is what is power. What does powerful mean? Let's not confuse with every DFA is NFA is DFA or not. But for every NFA, you can draw equivalent DFA. And what I mean by equally powerful is from DFA. If you remember, you can only design DFA for regular languages, right? And you can similarly you can only design NFA for regular languages beyond this space of regular language. The NFA can also be not designed for such things. So this might be, you might be now curious about what is beyond that regular language. So we will also discuss that. What is beyond this regular language, which DFA cannot do, even NFA cannot do. How to deal with infinite states. No, so all this is finite state, right? So these are finite states machines, and so the number of states are finite. Number of states may not be infinite. How do you deal with that? So here, the NFA and DFA both are equally powerful. We will see this theorem which says that every non-deterministic finite automation has an equivalent deterministic finite automata, and the other theorem is a language is regular if and only if some non-deterministic finite automata recognizes it. Right. So these are some of the things which we will discuss tomorrow. And we will also learn how to convert NFA to DFA very simply, and we will also revisit some of the theorems like union of regular languages is union and so on. And yeah, so I think we should be able to do this, and then we will jump to regular expression. Yeah. So this NFA, though it looks like it is doing a lot of things and it's magical, but it is not much more powerful than DFA. Okay. So with that, we will stop here. Tomorrow we will be doing all this, and then Monday we will have a quiz on whatever covered till tomorrow. Okay, and the Monday quiz also will have one or two question on paper pen. It will not be. It will not be. It will not be purely MCQ. So there will be there will be some question on MCQ and one to question where you need to draw it on paper pen. Okay, so NFA is on quiz is no on yeah. Two part of quiz. One will be. Oh, so NFA is not God really. Okay, so NFA is demigod. It looks like God. We will learn in this course. There is something more powerful than this, and we will do that. Okay, where we need to submit. It will be on Google Classroom, right? Okay, so a lot of discussion. Good to see. Okay, see you tomorrow then, and let's have fun.